I'm a machine learning intern at Whirlpool. And at Whirlpool, we create chatbots to automate conversations. So today we'll be talking about Namesy. So it's a name extractor we built at Whirlpool, which is customized for personal problems that come with chats. So on my first day here, I was confronted with this. And the problem was simple. Whenever a chatbot asks you what is a name, you have to understand what the person is replying. But as an enthusiastic kid, I went that's easy. I can just write a function from Spacey or use some library, write a name extractor, and my work will be done. But I was wrong. Like me, we don't understand that names are complicated because of certain things. Like we will have to deal with names that are from different countries. You'll have to deal with when people are not using accurate grammar. You'll have to deal with various other things. And that was just not an import library and work around it properly. So this was the main checklist. One, the model had to be multilingual to support all the languages from various countries. It also had to understand if the language model is English, but a person is from Spain or something, so it had to handle all the Unicode characters. It had to be grammar agnostic. So when a person says me is Meghna, it had to understand Meghna is a name. It had to understand random capitalizations are a thing, that people don't use right capitalization when writing a sentence. It had to handle emojis. And the most important thing was it had to be less than 2 seconds, including the network latency. So the upper cap was the predict function should be around somewhere 500 milliseconds, and it can't overshoot that. And that's how I started with the NLP libraries. So the first thing we tried was Spacey. Spacey was faster, it's easier to use. It also has really good APIs that you can build your code around. And this is where it excels. So when you give it a structured sentence like my name is Michelle, it is able to find the name and at a really good speed. So remember our cap was 500 milliseconds. At this point, it's able to predict the name in less than 500 microseconds, which was brilliant. But it was not all nice and friendly. So this is where Spacey fails. So whenever you have non-anglicized names like Meghna, apparently I become an organization. Or something like this, when the capitalization is not accurate and it doesn't identify it as an entity altogether. Or when you use something that is of this style, where capitalizations are randomly put into the sentence, and I call this the SpongeBob case. So it's again not able to recognize an entity. So let's recap what Spacey works for. It is really good when it comes to speed. It is multilingual, it supports around 49 languages, and it can handle emojis and Unicode characters. But does it work for chat? Not really, because we want the model to be grammar agnostic. We want when people type their normal, in a sentence in a conversational manner, it needs to be accepting of the name. So then the idea was we had to create something which will be able to understand how people type. It should be case insensitive, it should be grammar insensitive. And we decided to start with some naive baseline. So a model which is just fast and dirty and which will just work when you give a sentence. And we decided to work with something which was a normal classifier. And why use a dumb baseline? Andre said so. So Andre is a director at AI in Tesla, and his idea is first go in with a dumb baseline and then work your way ahead. And that's how we started with fast text. So why fast text? One, it's fast. Two, it's extendable. So it has pre-trained vectors for a lot of languages, and it satisfied our need for all our 11 target languages. And it is nice and easy to use. This is how fast text works. So when you give it a sentence, it loads the word embeddings that are already there on fast text. FastText has pre-trained word embeddings. Then it average pools these word embeddings, and then it uses a linear layer to predict whether all the classes. In our case, we wanted it to be a tagger to tag a sentence giving what is a name and what is not a name. So in this case, we pass the sentence sequentially token by token, and try to predict like what is a name. So for example, my name is Meghna. My should be not a name should be not a name, is should be not a name, and Meghna should be name. So that's how we converted fast text into a tagger. And you can see why it's pretty dumb. So the accuracy of the model was around 54%, which is not completely random because names are not, like names are really unique, but it had like really low precision. So whenever you said something like, so we had this example like that came across was, my name is Adi. I'm planning to build a restaurant and I'm looking for advice regarding like branding and logo. So the model predicted Adi, which is good, but then it predicted the name is Adi Restaurant Branding, which is not something we want. Like that would be a good name for his restaurant, but not something we want. So in this case, these were the problems that we came across with fast text. Its accuracy was not that great. It was terrible at rejecting garbage values. So if you type anything from your keyboard, even if it didn't make sense, it would consider that as a name. And the word embeddings were large. So for every language, the word embeddings were around 1.3 GBs. So they would take forever to load, and like even while deploying, we had to load every single thing again and again. So the key ingredient here was we needed to bring context into the concept like matter. So whenever you say sentences like my name is Meghna, you know that after certain words, they're going to be nouns or proper nouns. Like linguistically speaking, context is really important when you're like trying to understand how a sentence structure is formed. So this combination of LSTMs and CRFs really helps. So LSTM adds like a memory unit to it where it understands what the previous token was and the previous token to it was. And CRFs are really good at sequential tagging. So once it knows like tags of like previous X things, it can easily predict the next tags. And instead of building this like from scratch, reinventing the whole wheel, we decided to go with Flare, which has a pre-built LSTM and CRF modules. So this was the benefit of using Flare. It was retrainable. So we could take any data set, we could use any language and retrain it for our own purposes. It had context into consideration, so we didn't have to worry about that again. Its speed was not as great as Spacey or fast text, but it was still like under 500 milliseconds. The accuracy was still not that great because Flare faced the same problems as Spacey, that it was trained on a very structured conversation, and it wouldn't do well when it came to like you type like grammar agnostic sentences, and it was grammar sensitive. So we decided to reinvent Flare for like our purposes and change it, like tweak it a little bit so that it's beneficial for cats. So first part of it was improving the performance. To improve the performance of CRFs, we wanted to reduce the search space. So NER tags would be, there'll be a lot of NER tags, like it will try to find organization, and in this case we tag everything that's not a name, like any grammar prepositions, adjectives and all of that as not a name, and only person names as names. So this reduced the search space and it was more efficient at predicting. We added a lot of data with only uppercase sentences, only lowercase sentences, only sentences with like title case or like mocked up cases like this one, and this increased the data by around 20%. And then we worked on the engineering side of it. Like the model had to be fast. So whenever you come across a very common sentence, like again, my name is Michelle, here we know that my name is definitely not a name. And we know that these are going to be commonly used terms. So we created a stop word dictionary here. And every time these words came into the input string, they were detected before it even hit the model. And for the names, we had like Bloom filter, which is a probabilistic data structure. So we had like around 2000 most frequently used names. And whenever it came to that name, it was again predicted before it even hit the model. So this is how it looks on our previous examples. So when something is there like my name is Michelle, we know that Michelle is a common name and it was detected even before Flare in a Bloom filter. Then something like with emojis or like mocked up cases, Flare found the thing because it had the context during its training. It also performed really well when we tried it with like garbage values. So here NN was like not name tag, and whenever we type something like 40 or XXX, this case was important to handle because people will, if you ask them for their name, people are going to be lazy. They're just going to type something in so that they can move forward with the conversation. They just want to get the information. But your customer is not going to be happy with it. He's going to be like, I can't talk to XXX. I can't reach out to that person when I want to contact him further. So the trade-off was here, like whether we want to go for speed or accuracy. Because if we wanted to have a model which is even more accurate than this, we had to understand like the latency is going to be high. So in this case, our speed was around 16 milliseconds and the accuracy or F1 score was around 0.88. So if there was, this is how the English model looks like. So we use ROC curves to break the types between different models. So here you can see like the more area that's covered under the curve, it's better. So the model will be better at generalizing the results. It will be better at like understanding when you give it unknown words or text. And the recall you can see has taken a hit compared to a fast text model, but its precision is really high. So the recall is around 0.83 and the precision is 0.94. So in this case, it is very good at rejecting like what is not a name, but it might actually miss out some names. So that's, I think, a fair trade-off to make. This was the Spanish model. Spanish model, and all of these were trained on universal dependencies data set. So here it was, so with universal dependencies, you have data sets for a lot of languages. So whenever you want to retrain the model on a newer language, you just had to change the language name in the script and you can retrain it. So, and that's how the French model looks like. So currently for NameZ, we have like 3 languages, English, Spanish and French. And if there is like, these languages are captured by country code. So when you see a person's country code, you just take a list of all the languages available in that country. And if it's in the supported language, use that language, or else just fall back to English. And so the code is like live right now. So who wants to try it? Any names?
That's where I. You should have typed the full thing.
Yeah. Okay. So yeah, and it's also good at like whenever you type a garbage value. So it will keep asking for you to give your name or like type it in a text box whenever it gets an invalid name. So that's all. Yeah.
So my question is, so you now are accepting the way once you address things like for instance, my name is Meghana, you can answer the main part, right? So it recognizes hello Meghana itself.
No, so hello part is already there in our code.
Correct. I think so. One thing that you probably could do is just like how Alexa does, right?
Yeah.
Saying that may I address you as Meghana itself.
Okay, yeah.
Maybe that's like
yeah.
That's like a feedback.
Yeah, so it will be fun.
Yeah, you can do that. No questions. Please try to record.
Thank you.